Thanks for your interest in our paper, Real-Time Edge Template Tracking via Homography Estimation. The goal of this paper is to track a given edge template through the whole video sequence by estimating its homography transformations. The motivation of the using edge template is to handle difficult cases such as non-Lambertian objects like the disk contour in Figure 1, hollow targets like the hexagon contour, textureless objects like the box ring, and thin structures like the ring contour. The difficulty of tracking these targets is that there are no rich or stable regional informations. So, we propose to track these targets using only edge informations. Figure 2 shows the whole workflow of our edge-based tracking. The core of our method is to estimate the homography transformations between two consecutive frames. The method mainly contains three parts. First, given the to-be-tracked edge template, manually initialized in the first frame or tracked from the previous frame. The first part is to get the feature map F. The given edge template is represented by a binary edge map T. We compute the distance transform of the edge map T to get the distance map. But the distance map is relatively sensitive to outliers, so we compute the feature map F from the distance map as shown in Figure 2. The second part is to get relatively clean edges from the incoming frames. When the new frame I comes, we first detect the edge segments from the whole frame, then we remove the irrelevant edge pixels according to the buffer region of the tracked edge template from the last frame. The retained pixel EI are organized as a set of edge fragments. Each edge fragment is a 1 pixel width chain with edge pixels sequentially ordered. The third part is to estimate the homography transformation between the feature map F of frame I-1 and target edge pixels xk of frame I. We formulate the homography estimation problem as a minimization problem, similar to Lucas-Canada method. But the cost here is not the sum of the square differences of corresponding pixels intensities. Our cost has two parts, alignment term and smoothness term. The alignment term is actually the sum of the element-wise multiplication of the feature map F I-1 and the binary target edge pixels. The smoothness term is the sum of the differences between two adjacent target edge pixels corresponding values in the feature map. WXP is the homography transformation of edge pixels X, and P is a vector which represents the homography parameters. Gauss-Newton gradient descent method is used to minimize the formulated cost function. The experimental results show that, first, our tracker performs well on textureless targets, such as hollow targets, thin structures, and non-Lambertian objects. Second, our tracker is real-time in CPU implementation, about 30 frames per second. Third, our tracker is promising in real-time computer vision and robotics-related applications, such as augmented reality and visual surveying. The top right video shows the tracking results of our method and other relevant methods.